Okay, cousin, do you want to introduce David? Sure. Very pleased to have David Fernandez Rivas here with us for the whole week. This is his first day in Boulder, and he's visiting us from the University of Twente in the Netherlands. David is a nuclear engineer by degree, but has moved on to maybe, I don't know what to say, microengineering, and does really cool stuff. But what I believe David's going to talk about today is related to a book that he wrote on empathic entrepreneurial engineering. He takes a very interdisciplinary approach to leadership and education, including empathy and entrepreneurship. He's the founder of multiple companies, including one that won an award at CES last year in Las Vegas. Ooh. For a needle-free injector that I'm extremely interested in for smart tattoo research. And yeah, just really excited to have you here, David. Thanks for giving us a talk.
Well, thank you. So I don't know if I should stand or sit. I'll probably stand. I'm not used to sit that long. And it was a long flight yesterday. I think my wife told me I was traveling for like 24 hours. So a bit of standing would not mind. So it's a small audience, so probably stop me when you are interested in having a question. So maybe interesting to highlight that recently I also joined as a visiting professor at Regenerative Medicine Institute in Maastricht. And I'm also visiting professor at the dermatology department in Rotterdam. It's the biggest medical hospital in the Netherlands, and I think one of the biggest in Europe. And for more than 10 years now, I'm affiliated to the mechanical engineering department at MIT. Okay. Let's see if this works out. Yeah, so thank you. And I wanted to say that I feel also close to home because even though I'm from Cuba, and just this morning I saw that here you have also a place called Netherlands, which is the Netherlands. So it doesn't really feel that I had to travel, to the other side of the world. I normally like starting with some sort of questions to trigger, and then in this case, hi, welcome. So I would like to ask those here, and maybe I can see when the camera now is off, if you get some impulse or some feeling when you see an image like this. So please raise your hand. I'm trying to remove that little thingy on the top.
Yes.
But
to the right. Okay.
So this is a dexterity text. No, I cannot get to the okay. No. But, yeah, this is more or less. Well, don't worry. Yeah, I don't know how to get there. I mean, I move my mouse there, but this meeting is transcribed.
Yes. So where to the left or to the right?
Yeah, but the mouse is under that menu. So now it is. Click, yes.
Okay. Now we have to do the human.
Yeah, well, it's just more to. Well, I can go back and do.
Is that really the human part? All right, fine.
No. It's just for fun. That is just.
That's on your screen.
Yeah, that's part of my story. So I want to. If you raise your hands. Exactly. So typically, you might be surprised. Sometimes I have audience that are like they don't really show much connect or empathy or sympathy, but I like to trigger this again to check that we are among humans.
Yes.
And one of the reasons why I think many of us in engineering work have been focused for many years is on how to tackle this one. And when I'm talking to master's or bachelor students, if I would be in their shoes nowadays, I would feel overwhelmed because these logos are cute, but when you click on any of them, you get an avalanche of websites and documents and reports and blah, blah, blah. And then where to start? So typically in science, we start with small steps. And I don't know if you're familiar with Richard Feynman. I have seen a few pictures around, so I think I'm preaching to the choir here. But small is also, small is beautiful. It's a kind of theory that has been advocated for a few years now. Appropriate technologies, better alternatives. And I also saw around that, you also talk about technical is beautiful. So with this talk today, I want to convince you that microfluidics is not only small, but it's also beautiful and useful. All right. So I hope that people in the audience will be able to interrupt or ask if they have a question. In short, my CV, I have a longer talk when people ask me to tell how a Cuban ends up in the Netherlands doing research. After I finished my PhD, I started my first spin-off company, Bob Clean, and I brought here later if you want to see the product that we are commercializing, and started with a microfluidic chip for ultrasonic cavitation. Very recently, I graduated a second PhD student in electrochemical aspects, so making electrodes for hydrogen production more efficient. We are trying to start up a company here, but it's a bit tricky right now. But what I will like to share with you is more or less as a journey on this needle-free injection approach that Carson was just mentioning. And we are exploring different alternatives on how we can exploit this microfluidic technology, but I will focus today mostly on flow beams. But first, I would like to begin with a little video here. Let's see if the audio accompanies us.
To boldly go where no man has gone before.
I don't know if you are into Star Trek. Here, Captain Kirk getting a needle-free injection from Dr. McCoy. And sometimes I drop the question, like, why didn't we get needle-free vaccinations during COVID? So the answer will probably be dropped later on in the slides. I would like to now, well, you already saw science fiction. Since I was a child back in Cuba, I've always been dreaming with, Star Wars, science fiction. And I was reading this book 1 or 2 years ago by a Dutch author there about, lightsabers. So in one of the chapters, we'll leave it there. I saw that there was a chapter on the hypospray. And when I finished this little chapter, so it's in Dutch, but you can probably read here that one of the references is a patent that I wrote. So for me, it was like, wow, I'm already part of the science fiction literature. So that was, very exciting for me. And so what is the science fiction engineer for me? Is, well, somebody who matches knowledge and ingenuity to practical challenges, never stops learning, but more important, I tell my students, you have to become a teacher in a way, because if you get your diploma, when you get into the work floor, you have to teach and train technicians and other people. It's a connector, so typically academicians are accused of being in an ivory tower, and I think that typically is not the case. Most of the people I know are very well connected to society. But still, this might be too blah, blah, blah for students. So I typically say, I would like you to focus on 3 main ingredients, KPE, instead of KPI, in the business and marketing stuff, they talk about it. So knowledge, everybody agrees. Yeah, well, that's why we come to university, to acquire wisdom and knowledge from our professors, we hope. Persuasiveness, and we will discuss a little bit more what I mean with persuasiveness, which is not be confused with manipulation. And empathy, which I will explain in a few slides what I really mean with it. So I promised I would tell about flow beams and the bubble gun. So it's a technology to inject without needles. But you saw empathy also has been in the Blade Runner movie, like a machine to measure empathy. I haven't been able to build a machine like that because as an engineer, I like building things. But I have a small method that I'm implementing in my teaching and uses this knowledge, persuasiveness, and empathy framework. So whenever you're starting a problem solution path or you're trying to understand something, you have you or your team, and then you have the user or the stakeholder that has the problem. So you can map a very simple, like chessboard like this with only 9 blocks and start like where you are, where they are. Ideally, you would like to reach a midpoint. But if you treat, whoever stakeholder you're talking to, like, they are there and we are here, and you don't build that rapport, you're probably going to face some resistance. And I have some example now. Another question to the audience. Who of you have had a good idea today? Could also be a bad idea. Nobody? Yeah? Whatever. This is free thinking.
Well, I just said I want an AI agent to help me solve the connection problem.
Okay, well, so typically, let me see now if I can click the right thing. Well, every day we are full of, hi, welcome, come inside. Hi. Hi. So you can get closer. I don't bite this early, closer to lunchtime, maybe. So typically you might have a great idea and then it comes up into your head because you have some sort of knowledge or you have experienced some sort of problematic situation, and or it can come up this idea in a small group of people. So typically in the engineering or the STEM disciplines, we tend to work, alone or in small teams, and maybe your empathy or persuasiveness ingredient levels were not so important at that moment. But slowly, you probably need to at least persuade other people to hear you out. Maybe you also need to start, evaluating if what you have thought has some sort of potential to be deployed into society. And then at some point, you really need to maximize your persuasiveness and empathy to get, the right team, the right funding, because there are many ideas out there, and you typically need at least 2 of these 3.
Oh, sorry.
Well, I mean, then you are golden. But if you have a good team and a good idea, eventually the money should show up. If you have a good team and a bad idea, with money, you can always figure out a better idea to work on. But the real test is when you have to really get people to buy or to use the technology. And it should be based on persuasiveness and not manipulation. And why I'm stressing this is that if you have only one of the 3, you might get in trouble. For example, if you have no knowledge of what you're saying and you don't empathize with the customers or the user, you might blah, blah, blah your way through, so BS your way through, but in the long term, it's going to bite you back. So there's this very famous case of Elizabeth Holmes in Theranos story. I mean, dropout, didn't know much about the patents that she was even an author, and the empathy for the patients that got fake diagnostics is very painful. So I typically say that if you have only one, like persuasiveness, you are more like a politician. Yeah? You might probably not empathize with people who didn't vote for you. You probably don't know much about what you're saying. But there's also danger if you only have knowledge, in the sense that if you don't reach out and exchange ideas with other people, your ideas get there and will never see the light of day. If you are too empathic and you start crying when you see images of contamination, like the robot test that I had there, it's a pity we could not test it with the colleagues later on, then you might suffer because you don't have the knowledge, or you cannot persuade somebody to hire you or to help you solve the problem. So ideally, you need to have 2: knowledge, persuasiveness of empathy. Why I say 2 is that if you are not very extrovert and you are, an inventor of an idea, with some persuasiveness, you can ask some colleague or friend who's more, outspoken, more extrovert, and then he can become or she can become the face of your company or your salesperson. Well, enough of this story. This is in academic settings. Looks like a very interesting cycle. In reality, I think, Carson, I don't know if any of you have been involved in other spin-off creation company. It's a mess. But in academic settings, we need to at least create some sort of milestones or a post that you can get somewhere. So if you want to know more about this, I wrote this book, and there's a little video here. I have another test. I have a lot of questions for the people in my audience when I give presentation. So let's see if any of you spot. There are 2 superheroes here in this page. 1, 2. I don't know if you can spot who. The mantis? Okay, so I'm in the right audience. So most people might spot the Black Widow because it's, former KGB agent, good martial arts. So the skills are very recognizable in the Hollywood entourage or Marvel universe in this case. But the mantis, what is the main power of mantis?
She can read people's emotions.
Exactly. So empathy. So soft skills, which are hard to get, is one of the less popular skills in engineering. So in this book, if you are interested, which by the way, I'm using in my teaching, and one of the prologue was written by Bob Langer. He's a prof in MIT, also known to be very entrepreneurial. And I use it for my teaching. There's a chapter for teachers. It's a rabbit hole. So if you're a student, don't get there. But I also have some examples because it's not only about me. I went and interviewed other entrepreneurs that are not necessarily the typical entrepreneurs you see in the media. For example, Connie, after getting a PhD in the Netherlands, she went back to Uganda, where she was born, and started a small business to help rural teachers to teach better. Miguel Modestino and, and Daniela, after her PhD in NYU, she started a machine learning company in the chemical engineering sector. She was actually featured by Netflix in one of these programs a few years ago. And these guys are doing one of the coolest things. I think now staff is in the news for a new company on nuclear waste management. But back then, I think he's already out of this company. They were producing at the beginning vodka from air. Yes, alcohol. But then during the pandemics, they start doing hand sanitizers, and they landed a big deal with the aviation industry. So now they got funding from the U.S. Air Force and I think Blue Origin, I don't know. So why I put this is that no matter in which activity you might want to innovate, there's always room for innovation and creating value for society. Now, as a teacher, I think, well, I don't know how many of you have already faced this situation. We need to provide education for all different, backgrounds, disabilities, and we need to create the Homo Universalis in a record time. When I was a student in Cuba, in 5 years, you will get your engineering degree, and masters and PhD were just like exceptional. But nowadays, at least in Europe, bachelor is only 3 years, typically chopped down into trimesters, where I get the feeling that the students don't even manage to get in depth about anything, and then you move directly to the masters. So what I think here is like, how can we learn from the past how to be more innovative, more effective? And then if you look in Wikipedia, which are the inventors that are known now in society, you might wonder, where are the women? I'm not the only one. I was just running this morning, and I found here that is the Hair History Month. So luckily, there's an ongoing movement to try to bring forward the role of women. And I think I have a slide in a few moments that illustrate why, for me, this was a surprise. But then if you continue looking in history, how people in the past used to solve problems. So you see back then that the world was relatively small for an inventor. No? You might be trading some doves or messages with some other philosopher, but slowly as the world start being bigger and the complexity of problems increase, the size of teams also increase. To a point that I think it has been established that the world is round, even though not everybody agrees with that, but the teamwork importance has just increased. And that became evident during the pandemics. Teams, pun intended, with the communication in distance, but the challenges still remain, because it's not only the physical world that has challenges, the online, our way of thinking about technologies. This is a map of the online world. You see Google, you see Facebook, the dark web. So check it out. This I took it a couple of years ago. So I can imagine now the continents or the countries have shaped a little bit, but Amazon. But now, why for me this has been a revelation? Welcome. I was studying in Cuba, and both my bachelor and master's supervisors were women. So if something positive the socialist project in Cuba had is that women were given equal access like many other people. And I have been grateful, lucky enough to collaborate. These are some older pictures from the team over the years. I have many other pictures, but I typically try to look for a balance not only on knowledge, background, and that's my answer to how to solve these complex problems. But before we move on to some other examples of the technology that I'm developing, I want to establish with you what innovation is. And I would like to ask your opinion if you want to share.
I would think that like the way that I see innovation is when it's like you're seeing things in a different way through a different light. It's not like inventing the wheel, but it is really looking at connections that were not looked at before.
Yeah.
And like it might solve a problem, but not necessarily.
All right. Anybody else would like to Share. Right. So why I use this smoke? Because in the words of politicians or big business people, it feels like smoke. No, my humble definition, which aligns with almost anything, is when you change something that already existed or you modified something. And I keep having that when I think I have a great idea. Sometimes you Google and then you don't find much, but then a few months later, you find an article from the Soviet Union that has been recently translated, and then the idea was already there. So I agree with you. We sometimes get lost in this idea of groundbreaking and, but well, an entrepreneur. I think in US, this definition might be more used in society, but you might be surprised in Europe or in Netherlands. Sometimes it's a term that is, seen as negative. For you, what is an entrepreneur? I know, Carson, you had also a spin-off company.
Somebody who is comfortable jumping into things where they have no idea what they're doing.
Okay, that is it fits in my in my view. Anybody else would like to share the ideas?
Sounds like a risk taker. I was.
Yes. So we're in the same wavelength. So indeed, you're taking risk. You're risking, being ridiculed by the market or ridiculed by nature, because sometimes you might be trying something that is not going to work at the beginning, for sure. You might lose your credibility if you are an academician and you spend 5 years trying something and it doesn't work out. And you might also burn a lot of resources. No? And I put here the younger people, because the older you get, time is a resource that is more and more scarce. And what I want to stress is that it should not be seen only for money. There are enough examples of entrepreneur when you already do it within an organization. And the 3 examples I gave you earlier of capturing CO2 from air and making ethanol, training rural teachers, and using AI or machine learning for the chemical industry. In my courses, if you are interested in how I teach this, I have also some activities, so feel free to drop me a line. And of course, I have some more philosophical graphics and arrows that I know are very common in the field of pedagogy and challenge-based learning and all that. But I promise I will tell a bit more of my work on trying to inject without needles. And this is an old picture from the original team in which we started the project Bubblegum with funding from the European Research Council. And so basically the bubble gun refers to having bubbles. So you see here in the left, let's see if the pointer comes there. Yes. So on the left side, and then also because, I don't know if the people online are having difficulties in seeing me here. And then I will try to bring you in a very short journey. I have many more slides that I would like to show you, but I had to keep it short so that we can have more interaction. And of course, I'm professor at the Mesoscale Chemical Systems group. So most of what I'm showing you has dual use, not necessarily for military purpose, but needle-free injections for the bioengineering, biomedical, but also for physical chemical processes in the microfluidics, like chemical reactions. Oh, well, needles are a problem. I maybe should warn, I have 1 or 2 movies that a needle is soon penetrating some skin. I know I have to put a disclaimer for some people who have problems there, but you see that there are many types of needles and not all are a big problem. No? Some of them have been very successful in delivering drugs, but many people are afraid of them. But more important, we generate a lot of waste. Even before the pandemics, this is a number that was underestimated by the World Health Organization about needles only in health applications. So imagine in the cosmetics, how many more needles are used, disposed, and less known, but equally relevant, very well-trained cosmeticians, nurses, and doctors every now and then prick their fingers. And this can cause severe problems for infectious diseases. Now, needle-free injection is not new. Already in the 19th century, there was the first patent, which was never exploited to inject without needles. In the 50s and later on, the US started mass vaccination campaigns, which eventually were banned for a while because the World Health Organization realized that you had to clean the injector in between people. And this seems like logical for us now, but you should not forget at the beginning of the 20th century, still needles were reused, for injection or blood extraction and stuff. So now the cool thing is that, as you will see here, there are many ways to inject. This is more or less the story I will be telling you in a moment. And here you see the technology readiness level value. So we are still in development. So I'll share some of the stories there. So we are focusing on using lasers to inject, to generate the bubble. So that's why the bubble gun. But there are other technologies out there. And why this is interesting for me is that traditionally, most people thought that you have to inject in the muscle, like insulin. Until recently, everybody was injecting with a big needle in the leg. But probably you have seen developments in having sensors and some artificial pump, insulin pumps or artificial pancreas pump, because it has been known now that when you inject insulin in the superficial layers of skin, it works better. The same has been demonstrated over the last few years that for vaccines and for allergy testing, you also have a good opportunity to elicit the same immune response with the vaccine if you inject superficially and with less volume. When I didn't have funding, I started here. And this is one of the reasons I reached out to Carson. And I think I have a couple of slides from like 10 years ago. Now, what if we could inject into the skin, like, I don't know if you have seen in Japan, there's an employer kindly pushing. Yeah. So imagine if we could bring drugs and medicine to the skin like that. The alternative we have nowadays is having a bulldozer bringing everybody in. When I was collaborating with the cartoonist here, there was a bit of blood on the floor. I said, I better not. But this is more or less the metaphor I like saying to people who are not into drug delivery technology. And this is the basic concept. We use a laser to create a bubble inside a microfluidic chip. It's very small, as I said at the beginning. And we generate droplets that fly at high velocities. This is a cartoon, but I will show you now how it works in reality. This is one of the microfluidic chips. That's a microscope objective. This is a 1 or 2 centimeters approximately. And this red rectangle you see here, for the people online, let's see here, that's this red dye. And then the film you will see at the bottom, the counter will tell you that in less than 1 millisecond, all the liquid will penetrate this gelatin. It's transparent because, as I will demonstrate later on, visualizing these experiments in skin is a bit tricky. So you see now how in 0.3 milliseconds, the liquid starts penetrating here. And then the challenges that I will tell you, some of them in the coming slides, is to make sure that the payload or the liquid penetrates at the right depth. Now, as an engineer, I've been trying many different things. So from this menu, I'm not going to show you all of it. I will just highlight 1 or 2 of these experiments. So if we look at how the bubble is made, for many years, I got the question, are you damaging or destroying the medicine? We measure with 1 liquid and we didn't detect any damage. But recently we applied for a new patent in which we use 2 liquids that are immiscible. So the one that we're going to inject is not the one that we are heating. So you can see here how it works in reality. So that liquid droplet, which is quite long, as you can see, is similar in cross-section. The diameter of this little droplet is similar to the inkjet printers that you all have in your offices. But the difference with what we do is that these velocities are much higher, and we make very long jets so that you can really penetrate. So fast forward, you can put there different type of liquids like polymers, and then of course you can get different results. In this case, we're tracking the velocity tip here, and then it starts slowing down when you increase the concentration. And at some point, you start seeing these lighter lines corresponds to the formation of beads and strings in polymeric solution. This is very known in rheology, so you see here at the bottom. And this is just to illustrate the versatility of this technology, that you can really jet out almost anything there. But now what happens when you start injecting into real skin? One of the questions I have in the audience, I know already one answer, but tattoos have been historically around for more than 5,000 years. So when I started doing research in this, I realized that there was a missed opportunity, not only to understand the physics, because there was almost no article explaining how the technology works, but also possibilities that I think, if you know Carson, we don't need to go into details, all the possibilities that are there with tattoos. So I collaborated with Walter Isaacson in this episode of the Trailblazers. I think now it's in Spotify, but it's fascinating. So if you want to know more and you haven't talked already to Carson, so this is an interesting. Now, what we did a few years ago is trying to validate, can this happen in reality? So we compare topical application, a tattoo machine, and let it wait, and compare also with our needle-free injection technology. So this is one of the warnings that there's a video going to inject into some real skin. In this case, it's porcine skin. And you see that the machine pushes the needle back and forth. And it's a very inefficient method to inject, because sometimes 50 or 80% of the liquid is left outside and only a small portion is left inside. When you do cross-section, no surprise, you find the entry point of the needle, which sometimes can get infected, so you can get a wound. And so what happens?
Is that traditional
It's a,
tattooing?
yeah, it's a,
What you're showing?
yeah, traditional tattoo needle. In this case, we move the sample with respect to the needle, but we also have some studies with the needle there for a longer time. And the interesting thing is that when you compare with our way to inject, we don't find any entry point. Of course, we don't go as deep as the needle, which was also desired. Where's my mouse now? So the depth here is a couple hundreds of micrometers. In this case, it was not optimized. So this is one of the things that we are currently working on. And I received even more funding to investigate how this happens in reality, because as I will show you, we have been learning a lot about skin properties, but still there's a long way for us to get there. Why this matters is besides recreational tattooing, which could be an interesting commercial proposition, there are many applications where you would like to inject without damaging the skin. For example, for allergy tests for kids, but also the best technology out there now for managing diabetes, the patient needs to replace every now and then the semi-permanent needles. And at some point you have the belly full with scars. So that is not the ultimate solution. And I think you're all younger than me, I think, so you might not be worrying about Botox, but one day you might. Now, the question is, how much do we really know about skin? And when I started this research more than 10 years ago, I assumed, yeah, everybody's covering skin, it has to be tabulated. We know everything about it. And the answer is yes and no. So we know a lot about skin on the regular scales that, and temporal dynamics that we, conduct our daily life, but at the micro scale and fast deformations, we seem not to know enough. So why that is the case is that, well, this is more like physics terms. It's opaque, anisotropic, poroviscoelastic, and changes with everything around. How much water are you drinking? What are the environmental conditions around you? So this is a very interesting, fascinating engineering challenge for me. And why this matters is that if you want to really develop drug delivery technologies compared to microneedles, the time of application of needles can be minutes to hours. Tattoo needles you see here in the middle, and a conventional needle, you have it there, they deliver the drug and then they pull it out, so it's still a couple of seconds. But what we're trying to inject is small volumes and in a dynamics that is super fast compared to any of the other technologies. So we need to characterize better, and surprisingly or sadly, for me, we have identified this rapid delivery focused cube that you see there. On the bottom floor of this graphic, you see the spatial resolution and interrogation area of some imaging techniques. So you have there laser droplet vibrometry, and here you see the temporal resolution. Some of these machines work very fine when you have transparent media, or you are interested on some properties that are relatively easy to get access to. But the other techniques out there, like acoustic or contact or liquid solid, really are scattered all around, or don't really fit inside this cube of rapid delivery that we need for these new technologies. Therefore, we have been making simpler experiments So in this case, what is the simplest thing that physicists or engineers can work with? A droplet of water. Also a spherical condition. You probably have heard a joke that physicists try to model a cow, and then they talk about the spherical cow. So here we have a droplet of water, and then you see how these jets penetrate just a droplet of water. And to me, this really looks like the Death Star. I don't know if you are into Star Wars. So I sometimes like to say that with my presentations, I can unite three branches of the science fiction community. Star Trek, Star Wars typically don't get along too well. And the Marvel universe is more for the younger generation. So I think we can all be together. The challenge with water is that you can see through, but with milk, which is opaque like skin, then, well, you don't see much of what happens there. If the droplet dries out a few minutes later, you see here we have like creme fraiche. And this is still a model for skin. And we can build with this model also numerical simulations to try to understand how this happens. But in reality, skin is a lot more complex. So we are step by step making more realistic models such that we know, for example, in this case, if the material is too hard, you get the splashback, which is not desired. In more realistic situations, you might get an injection where part of the liquid penetrates and another part pulls on top of the surface. And we have been mapping for a few materials where do you get the injection, which is the top left part. But for some other applications, like industrial coatings, you might want to also exploit a technology where you know exactly how the liquid is going to behave when it impacts the substrate. This was just published last week. We can use the same experiments to compare the properties of surfactants. So surfenol is one of the ultra-fast surfactants right now, commercialized. And we made an experiment shooting at a little cuvette where you can see, that with the surfenol, I think I took out the next slide, but I think Carson, with his chemistry background, might be interested in this one. We can characterize how fast these surfactants can move to the surface. So SDS is a very popular surfactant, behaves like water, but then surfenol is much faster. So it can rush to the new interface we are creating with the jet, and then we can characterize this. And this is a very interesting study that I started with some colleagues in Spain. And the same method that we are trying to develop to inject with our needles can help us characterize the properties of novel materials. But now, a small commercial, and I have to make sure that I don't.
Can you feel it? Imagine a world untouched by the sting of sharp edges, where healing flows without barriers, gentle as a breath. A world of ease, where comfort meets care and fear fades like mist in morning light. A place where possibilities are limitless and peace finds its way to everyone. Imagine a world without needles.
And in a moment, you can also interact with a mock prototype that I brought for you guys. So far, this is more like a cat annoying system. But in the future, all the technology that I was showing you there, so for the people online. So here you will have the drug. This is still a mock. It's not probably going to look like this, but then just putting it against the skin, you could, deliver a vaccine, or in a different embodiment, you could also tattoo without needle. So I'm happy to discuss those in a moment. Let me wrap up the story I had for you. As Carson said last year, this concept got the CES award. And over the years, we've been gaining a lot of attention from the media. During the pandemics, actually was overwhelming. And right now for Flobians, which is the name of the spin-off company that I also brought some goodies here. I will leave behind some pens. That's the commercial part. Even though this is our dream to deliver in the human pharma, we have received interest from the cosmetic sector. And that's interesting because the regulatory pathway is a lot cheaper, but it's a gray zone. That's academician. I have to be very careful on with who I associate myself. But now, going back at the beginning, how does this knowledge, persuasiveness, and empathy framework work for me in reality? So as we said at the beginning, I'm a nuclear engineer, so I didn't know much about lasers. And even though I have skin, I didn't know much about skin at the microscopic scale. In this case, I was persuaded by a colleague from Mexico to host a PhD student for 1 year in my lab because we have clean room facilities and we could fabricate microfluidic devices. And they wanted to test a novel technology back then, diode lasers, which are now in almost everybody's lighting at home. And then I said, well, why not? I knew already some colleagues, even in my own university, had tried pulse lasers, which are the bigger machine ones. And then I said, well, let's just try it. And when I saw the first results, I realized, hey, maybe there's an opportunity here. So I went out and empathized with tattoo artists, people with tattoos. I talked to endocrinologists, people with type 1 diabetes. And then I received a little bit of funding to organize the Fusion on Their Skin that I will show you in a moment. It's kind of an event where I invited people. We even had a tattoo live demonstration there. And all that information or the traction that I gained there allowed me to get a bit more funding. I visited MIT, got successful getting a few grants, which allowed me then to hire people and increase the knowledge and the whole, virtuous cycle of knowledge, persuasiveness, and empathy. And a couple of years ago, we organized the second edition of the Fusion on Their Skin, and I'm trying to organize next year another one. But what I want to highlight here, and I see around you guys build a lot of interactive stuff, is that the outreach is super important. And I have one example here, and I will say why. Well, safety is important, of course, so you always need to put the glasses. But you will see these two experimentalists doing is pushing a little pump with an enlarged version of the microfluidic chips that I have been showing you. And why I think and propose this type of events is that you can gain a lot of information from society. And to make one example very tangible, we've been developing all this technology to inject without needles. Everybody agrees. But then I think it was Reuters put in one of their websites a video of the interview. And there was this person, let me just stop this because it's a bit annoying. And he said in a comment, oh, fantastic. I like this. This sounds like hyperspray, Star Trek, blah, blah, blah. I hate needles. However, I'm also afraid of lasers. Which already indicates that as innovator, you always have to stay 1 or 2 steps ahead because you are bringing a new technology you hope is going to solve the problems of all these people, but every new technology can create concerns and risks that you might not be aware. So only when you get out of your comfort zone and show, and sometimes can be seen as you're showing everything. No, you need sometimes to let some things be visible because you will not get the feedback or confirmation that what you're trying to do makes sense. So that's why in the Fusion there are skin, and you can see not much has changed here. We had there a bit of art, a live tattoo demonstration, professors, directors from institutes coming up, and we had a very interesting debate. And then a couple of years later, we organized this second one. The third one, I'm planning to do it in a more centric place in the Netherlands because we are like 2 hours away from Amsterdam. And for you guys in US, 2 hours is nothing, but in the Netherlands, 2 hours is a long distance. And well, I believe that united, as a team from different backgrounds, we can develop this technology. And I don't know how much time I still have left, or because because we can talk more about it, but for you to see how this knowledge, persuasiveness, and empathy works in practice. In another example is my first spin-off company, and I think there's also audio. So you can see the differences between a bootstrap spin-off company and one with more funding. So the other video was a lot more slick, but you also need to be proportional. No? I say ultrasonic cleaning is a dirty business, so you can also pass on and interact with the product. And needle-free injection has a different allure or meaning to society. And then here the story is that my knowledge there came from my PhD. So I was doing sonochemistry, ultrasound to create bubbles, and I did a small microreactor where we could study radical reactions and things like that. And then with that knowledge, I persuaded with a colleague of mine, our faculty to give us a bit of money, apply for a patent. We got out of the lab and start talking to jewelers. 3D printing in 2012 was a big thing. Nowadays, it's common. But you might be surprised how they were cleaning back then some of their stuff. So with that knowledge, and we got a bit of funding from the Dutch government, we created this bubble bag. And well, we persuaded some people and students to join us. So here now the company is a bit of in a latent mode. We are looking for a CEO or somebody who could really take the company to the next step, because right now with all this AI, new chips, semiconductor industry is really demanding a lot. So actually, I'm being asked to do more consultancy in this direction than in product development. But well, I wanted to show you how this knowledge, persuasiveness, and empathy also work in reality. And of course, I have to thank all the people that have helped me getting all this together, because of course, it's not my work alone. Here you see a mix of employees from Flowbeams and from my PhDs and postdocs. And with that, I would like to thank you for your time.
First question. I have lots of them.
Yeah, and I would like also if Bill, I see Bill or Michael, if they want to ask something, just unmute yourself and shoot ahead. Yeah.
I don't have any questions at this time.
Yeah, please.
You know, I'm saying I don't have any.
All right, thanks. So please go ahead.
Oh. So like for the bubble bag product, is this like, what is exactly causing the cleaning to happen?
Yeah, so we are creating these tiny bubbles from these pits or gas entrapment indentations you see in the inner side of the walls. Let me show here to the people online. So it's indentations we make in the inner side of the bag. So when you put liquid like water, similar to when you pour some carbonated water or cola or champagne on a glass, you typically trap some bubbles at the inner surface. When you turn on the ultrasound, from those entrapped bubbles, then we can generate a lot more bubbles than if you would have, you know, your usual way of doing ultrasonic experiments. So you generate a lot more cavitation with the same energy input that you will otherwise have. So when you have the bubbles close enough to a surface, and I have different presentation slides for that. If you want to know, we can sit in the upcoming days and I'll show you more about the physics. So when you have a bubble oscillating under the ultrasonic field in an infinite liquid, the bubble normally oscillates around its spherical equilibrium. But when it's close to a wall, then there's an asymmetry that the bubble is able to grow in one direction, but then there's too much liquid on the other side, and then there's a pressure field that pushes a jet against the wall. And that liquid jet can remove contaminants from the surface.
So then is this meant for kind of like, I'm just thinking about audience. This is like not for clothes or anything. It's more for small things like in a lab setting.
Well, you might be surprised. There are huge ultrasonic labs, like, you know, the size of this room, because you need to clean then industrial parts. And then this can help to really bring the bubbles to where you need them. Because in a normal ultrasonic bath, you might even have areas where there's almost no cavitation. So you might be cleaning too much in some areas than others. So this, you know, mechanism can help you make it more efficient and treat the parts that you really need.
I had a question. I really like when you mentioned skin being a very complex material, and yeah, I like that you started with water and then you're going to milk. What, I'm a student of material science, so what other landmark materials do you see going from a Newtonian liquid, some like a homogeneous water,
Yeah, yeah.
and then you have a colloid like milk, and then going probably some viscoelastic, couple more steps, and then finally we should study what happens in skin. So what are those model materials as milestones according to you?
Well, I started from both sides of the shore. No, so you have skin here,
Yeah.
and then all these simple materials. So slowly I'm trying to get to the midpoint.
Mhm.
So you explain a very nice progression, no, from the simplest to a bit more complex. What we're doing now is creating artificial skin. So we are mixing in Gelma or some of these hydrogels that are used in cell studies or organ-on-chip technology. So we are seeding them keratinocytes and first looking at how tattoo machine or our technology kills them or not. Later, you can start adding other cells like immune cells or fibroblasts to make that skin model a bit more realistic.
Okay. So you would be like, next step would be like a blank hydrogel and then infusing that with different kind of cellular materials kind of stuff.
Yeah, we already have some preliminary results on that.
Okay.
So if you are interested, we can also sit and I can show you some of the
Yeah,
work
okay.
there. Yes.
And you, I remember one word you said, poro-viscoelastic.
Yes.
And I know the distinction, but I want to hear from you, like, how do you see, like, I just know the term that those are two different things.
Yeah.
How do you see them influencing, kind of like this phenomenon that you're trying to?
Yeah. Well, the one that I can think of right now is when you get a normal injection nowadays, when the needle is pulled out, most people don't see it because the nurses are very fast and then they clean it and put a cotton swab on it. So typically the skin tries to recover its shape and part of the liquid is pushed out. So there's some sort of elasticity there that the tissue tries to recover there. So depending on the scale that you are looking at, skin might behave relatively simple if you use a big indenter like your finger and you do, a soft and small indentation. So, the collagen and everything will give back its properties. But at the scale that I'm interested, then we really need to start looking at the interaction between the cells, because the sizes of these droplets that we are generating are comparable to the size of the cells themselves. So you need to start thinking like a cobblestone type of street, that I'm coming with a hammer, and the hammer is big enough to the size of the mosaic or whatever that you have on the street. So all of a sudden, the properties there are very different than if you want to come with a bulldozer.
Okay.
And that's what we're now trying to investigate. How can we mimic the real skin with systems that are not so complicated? Because then we're talking about protein interaction, fibrin, how different type of cells, stick to each other. You have then immune system cells that are able to move around. The molecular sizes of the different drugs. Some of these vaccines now are exosomes, so some interesting, vesicles with a lot of interesting chemistry in there. We are doing experiments with antibodies and some of these exosomes to identify how are these, molecules going to penetrate? Are we going to damage them in the process or not? Yes.
Let's say ink or do you control it based on speed or just curious about how you control the text of the deposit.
Yes, so it's one of the questions we're trying to answer. For different liquids, you can use different energy wavelengths, laser energies, microfluidic design. The channels can be more converging or not. And then depending on the application, you can also control the distance from the point that you are generating and the point of impact. Why this matters is that for Newtonian liquid, typically if you put the skin too far, the droplets will start breaking too soon. But just injecting water might not be enough. So we need to characterize if you put there some surfactants or some other things, we need to always recalibrate our system. So did that answer your question?
Yeah.
Yeah, that's one of the parameters we can tune there, but viscosity, unfortunately, is not enough because, like polymers, like we were discussing, some of these polymers can add not only viscosity but also elasticity. So it becomes very interesting from a academic point of view, but in reality, it might be a nightmare.
Do you have to clean it between uses?
The idea there is that this kind of transparent thing you have there would be replaced in between uses if you are doing, for example, a mass vaccination campaign. But one of the embodiments of what we are envisioning is that it would be a auto-injector. So you would have it at home. So if it's yours, maybe you don't need to clean it that often. So the laser and the handheld part can last for years. But what you might be changing is just what is in contact with the person.
If you gotta vaccinate 100 people, you need 100 of these, but then you can autoclave them or something, just avoid the waste.
Well, you could think of having something that is either easy to sterilize or clean, or something that is biodegradable, so that after you've used it and you put it, in with the right settings. So these are things we are still investigating and trying to create a life cycle assessment to try to identify after how many injections with which materials we can compete against the needle. Anybody else from the online audience?
I have a question. Does it hurt when you inject it with your spray versus a needle?
That's a question I have answered partially, and we are planning to answer it in a more official way. Until now, in the lab with a few colleagues, we did it, and we didn't feel anything. There are a few reasons why. The first one could be that we are positively biased, so that we can never rule out. Therefore, we are planning blind tests and healthy volunteer tests to assess indeed pain, but then we need randomized trials and blind testing. But all the conversations I've had with experts in the field indicate that you should not feel anything. And the reason is that the liquid volumes that we are injecting are so small, and we are targeting such a shallow depth in the skin that the nervous termination in our skin that are capable of picking up the pain signal will never be recruited. And the analogy, I always work with analogies, is like with a mosquito. You don't feel when a mosquito is pushing its proboscis or the mouth into your skin. What you feel is the poison that they leave when they fly away. So the scale of our jet is comparable to the mouth of the mosquito. So you should not feel it.
Thank you.